All right, let's begin. So hey everyone, hope everyone had a good weekend. So last week we talked about generative models. I hope everyone enjoyed my lecture last Thursday. And this week we're going to go into two more lectures, both on reinforcement learning. So today I'm going to kind of set up the basics of reinforcement learning, go through some of the basic algorithms. And on Thursday, we're going to go a bit more in depth into reinforcement learning and also look at how reinforcement learning methods can help us in these multimodal problems like text generation, like we talked about last Thursday. So anytime, feel free to just type on the chat if you have any questions. So today's lecture, I'm going to give a very brief and high-level introduction to reinforcement learning. And most of this content is taken from some of these amazing courses at Berkeley and CMU. So we really want to go in depth into the reinforcement learning and look at more applications, look at more of the theoretical insights. Definitely do check out these semester-long courses. I'm going to try to distill the most useful information and also most of the applications to language and multimodal into these two lectures. So let's begin. So the main things that we're trying to cover today are first the introduction to reinforcement learning, setting up the problems, especially using this framework called Markov decision processes. It's a theoretical framework that allows us to reason about the objectives and the algorithms for reinforcement learning. We're going to look at some simple cases of MDPs, and if everything is known, that means that it's easy to solve, it's small in scale. We can actually solve these MDPs exactly using algorithms called value and policy iteration that I'll go into. However, in the real world, where a lot of things are unknown and a lot of things are really high dimensional, you can't solve these MDPs exactly. So also going to give a brief introduction to how we can use function approximation and neural networks to solve these unknown MDPs. So let's begin. So I'm pretty sure everyone's heard of reinforcement learning. It's this new research area that has particularly gained a lot of interest recently because of the combination of reinforcement learning and deep neural networks. So in this new area called deep reinforcement learning. And it has seen many, many successful applications in the real world, including self-driving cars. They use some aspect of reinforcement learning. Recently, they've been able to train these AI methods to beat humans at Go, a game that was long thought too difficult for humans to play, again, using reinforcement learning methods. They've been also shown to do really well on these Atari games, which require a lot of human dexterity, but AI agents can also be trained to get better than human performance. And likewise, we've also seen a lot of applications of RL in the real world towards building robotics for manufacturing, playing multiplayer games like FIFA, and also building robots that can effectively navigate in the real world and interact with humans. So what exactly is reinforcement learning? So some of you might have seen this diagram before. Here's a very general setup that everyone uses to introduce reinforcement learning. Essentially, there's two key components. You have an agent that is placed in an environment. And this agent is going to start from a particular state in the environment known as S0. That's your starting state. You can think of these states as parameters of the environment that defines where the agent currently is. So in my case, I'm currently at this particular spot. That is where my starting state is. And whenever the agent is at a state, it's going to take some action. And this action is chosen from a set of all possible actions that I can take to interact with the environment. So very simple cases are, going left, going right, sitting down, or standing up. These are actions that I can take. And whenever it takes an action, the environment is going to, in response, spit out two things. The first thing is a reward, R0. So a reward tells the agent how well it's currently doing in its environment, whether positive or negative, and at what magnitude. And the environment is also going to tell the agent what's the next state that it ended up into. So if I move left, maybe I don't observe any reward, and I move one particular set to my space to my left, that will be my new state. So this sequence of interactions from states, actions, observing rewards, and going to next states defines the trajectory of the agent interacting in this environment. And this trajectory goes on until whenever the agent stops interacting with the environment. So clearly, this is a very general setup. And let's just look at it in the context of one of its examples here. So let's just say FIFA, for example, because I love playing FIFA. So initially, you're going to start at S0 at kickoff. So you have all 11 players on each side, each in their particular positions. Those are the initial states. And what are actions? The actions will be, each of these 22 players either moving around, up, down, left, right, or, kicking the ball or passing to another teammate. So these are the possible actions that you might have. And what are the rewards then? So the rewards could be, positive reward if you manage to score a goal, or if you manage to successfully pass the ball to your teammate, or if you're able to successfully prevent the opponent from scoring against you. So here are examples of positive rewards. And maybe you'll get a negative reward if you commit a foul, or if you fail to complete a pass, or if the opponent scores a goal against you. So here are so again, this framework is very general. It almost encapsulates any form of interaction between single agents, multiple agents in their environment and observing some reward. So let's go a bit more in depth. So a Markov decision process is basically a way to formalize many of the terms that we just talked about. So Markov decision process consists of 7 terms. It consists of a set of states that the agent could be in. It consists of a set of actions that the agent could take. So whenever the agent samples an action, it must fall under one of the set of states. It defines a transition function. So if you're in state S and take action A, it tells you the distribution of next states S prime that you will end up in the environment. Most of the times, these transition functions can be deterministic. So if I move up, down, left, right, I will deterministically end up in the next state. But at certain times, it might also be stochastic and random. There's a reward function that is also given by the environment. So it tells you if you're in state S and take an action A, ending up in state S prime, what is the reward that I observe? You're going to see a start state. And I'm going to go into a lot more detail in discount factor in the 2 slides. So let's pause on that for a bit. And you're also going to have a horizon H, which tells you a total length of interactions between your agent and the environment from which you obtain these trajectories. So one important thing of these Markov decision processes, as given by the name, is that it must follow this Markov property. And this Markov is the same term that you've seen for hidden Markov models, Markov random fields. It essentially says that all the information I need to reason about my next states and my next actions should only be contained in the previous state and action. It should not depend on states before that. In other words, we should be able to throw away all the history once this current state is known. So just to give an example, so let's just say I am upstairs in my room, and my roommate tells me to go downstairs and get him an apple. So that is one natural language instruction that is given to me as state S0. So S0 might be my current position upstairs in my room, and this natural language description that my roommate wants me to go get an apple. So there's 2 possibilities of defining a Markov decision process as I go and get this apple. One thing is that as I'm going to go from my room upstairs down into the kitchen, I'm going to take all sequences of states that I'm currently observing, and I can define these states using 2 choices. The first choice is just to keep my position in the house. The second option is to keep my position in the house, and I always append this natural language instruction behind it, that I should go to the kitchen and get an apple. So you think about it, one of these actually satisfies a Markov property and one doesn't. So the one that satisfies the Markov property is the one where each state consists of my current position in the house, as well as the natural language description together with it. So in other words, what ST would be one step away from the kitchen, my current state, as well as the description that I should get an apple. That satisfies the Markov property because now I can throw away all my previous information, all the previous instructions and my previous states, and just condition on ST and AT. So on the other hand, if I just keep the natural language instruction at S0 and subsequently only contain my position in the house, then by the time I get to ST, I need to condition on S0 to be able to realize that I'm supposed to pick up an apple. Just a very simple example to show how we can actually turn something that maybe does not consist of the Markov property to something that respects the Markov property by propagating this information towards the later states. So this is quite important. A lot of, if you look at all these applications like natural language navigation and all, they're given these actions and you're supposed to follow these instructions. They just give it at a start, right? So technically they don't respect the Markov property, and they're not technically Markov decision processes, but it's something to keep in mind as you design these algorithms. So then what is the goal in reinforcement learning? So you've seen that you have an agent taking states, you have an agent taking actions and going to different states and an environment. The goal is usually to maximize your total discounted reward. So as you start taking states and observing rewards, I want to sum up all the rewards that I'm going to observe throughout my entire sequence of interactions with the environment. So that would be RT plus 1. So the reward at GT at a particular time step T would be the reward that you obtain in the next time step, plus subsequent rewards that you obtain at T plus 2, T plus 3, and so on. And notice that we're multiplying by a gamma factor here, gamma the first time and gamma square the second time and gamma to the power of 3 to the power of 4 subsequently. So this gamma is actually what we saw previously as the discount factor. So why do we need a discount factor? So there's a couple of reasons. One reason is that you can draw an analogy to economics, which states that money that I have now at this particular time step is more valuable than money that I am promised to get in the future. So I should discount whatever rewards I get in the future. In both theory and in practice, having a discount factor also helps us to reason about convergence, because it encourages our agents to get to the final goal faster instead of just sitting around and collecting rewards. So it's also useful in both theory and in practice. And if you look at what values gamma can take, gamma has to be between 0 and 1. Gamma close to 0, or even when gamma is exactly 0, you're basically foregoing all positive rewards in the future, and you're just trying to maximize your immediate reward. That would be myopic evaluation. And if gamma is close to 1, then what you're trying to say is that I care a lot about rewards in the future and might prefer really large rewards in the future and forego short-term rewards in the near future. So different settings of discount factor also allow us to design different sets of algorithms depending on whether you want to care more about immediate reward or long-term reward. So I have a question, someone asking a question. How do we condition on the initial state to maintain relevance of subsequent actions to the goal? So I think you're talking about this Markov property here. So if you just use the same example that I did, which is both states being the position in the house and the instruction that you're given, you can always just define your states as appending this particular natural language instruction up until you find it to be useful. So you always append it, then that would respect the Markov property. In practice, you can also use things like LSTMs and kind of assume that LSTMs have memory, so it's always capturing this information into future states. Hopefully that answered this question. Yep. So now we've seen what MDP is. We've looked at states, actions. We looked at the goal of maximizing this cumulative reward. So what do we actually want to do in reinforcement learning? So we actually want to define a policy in order to maximize this cumulative long-term rewards. So what is a policy? A policy is basically a distribution at a particular state over actions that you can take at that particular state. So having this policy will fully define the behavior of an agent. So a policy is basically like a map like this. So at every state, it tells you the action which you should take. So maybe here I want to go upwards and rightwards towards the diamond because that gives you the reward. And if I'm in a state like this, I don't want to go upwards because I'm observing really negative rewards. So policy fully defines the behavior of an agent. And our goal in reinforcement learning is to find out this policy that can actually maximize our long-term cumulative rewards. The policy is stationary. That means once you've trained the policy, it just stays fixed. You don't change it anymore. And is during learning where you want to start with a random policy and collect experience in the environment to actually obtain a good policy. Sometimes, most of the times, your policies are random. We'll see why we need that in a second. But as a special case, you can also reason about deterministic policies in very similar ways. So just to summarize, we've looked at MDPs. We've seen how an agent with taking actions and going into different states and an environment and observing rewards is a very general framework that encapsulates many of the real-world reasoning tasks. We've seen that the goal of the agent is to maximize its cumulative reward multiplied by a discount factor. And you want to learn the best policy, argmax over all possible policies, that best maximizes your cumulative reward. And each of these policies will define a particular distribution over actions that the agent should take from different states. So here's the main goal of reinforcement learning. So just to summarize some differences between reinforcement learning and supervised learning, in RL, we usually care about taking decisions over multiple time steps and observing cumulative rewards. While in supervised learning, we usually make a one time step decision and we're done. And because we're doing sequential decisions over multiple time steps, you want to maximize cumulative reward, sometimes foregoing immediate rewards and really looking at your long-term rewards that you might get in the future, But for supervised learning, you don't really care about future rewards. There's just a single immediate reward that you would like to optimize. In RL, you also might have this problem of sparse rewards. So again, if you're playing this FIFA game, if you're defining these rewards as having scored a goal, you're not going to observe that many rewards as you play this game between two teams. So that's a sparse reward problem. In supervised learning, you usually have very dense supervision. You have labels immediately. So you never really run into this sparse reward problem. And in RL, we've seen these MDPs, but these MDPs might also be unknown. So you might not know the full extent of all the states there are. You might not know all the actions there are, and you might not know certain rewards. So there's also a degree of uncertainty in the environment in RL, but you don't usually have that in supervised learning. But before going into RL, there's actually a very close analogy to supervised learning, which is called imitation learning, that I want to go through in just one slide. So what is imitation learning? So again, let's say you're in this agent in an environment. Let's say you want to train a self-driving car. What you can do is that instead of getting the car to start randomly, and that's going to be obviously dangerous, what you can do is you get a human driver to sit in the car and just drive it as a human driver would. And you can collect these video demonstrations of how the human driver drives the car. So human driver will start in state S. Maybe you're in your runway. You will pull out. You will turn left, and you would follow the road signs and eventually reach your destination. And we know that these are very good trajectories because human experts are driving them. So these are called expert trajectories. And once I have such an expert trajectory, I can basically decompose it into a supervised learning problem. So at every state S, as observed in this set of expert trajectories, just try to build a data set that maps S0 to your best possible action A*0 as given by the human expert. And these expert trajectories therefore give you a really large data set that predicts your expert action. And you can actually train a self-driving car using supervised learning to predict this expert action, right? By taking in maybe the image and building a neural network that predicts this set of actions as given by the human expert. And this actually performs reasonably well. This is a big class of research in reinforcement learning called imitation learning that leverages a lot of human demonstrations and human experts. But there's some issues. One issue is a distribution mismatch between training and testing. So let's say if I only collect expert trajectories of humans driving in the summer, they're not going to be able to train a model that drives in winter. It's also hard to recover from suboptimal states. So in this set of expert trajectories, all these states are perfect. It always stays on a road. It always follows the road signs because an expert are labeling these trajectories. But what if for some reason you make an incorrect action? Even if you do supervised learning, it's going to be imperfect. So what if you make an incorrect action and you end up on the curb? Then you're not going to get any information from these expert trajectories how to recover from the curb back onto the road. So it's not going to be able to recover from these suboptimal states. And also, sometimes it's not safe or possible to collect expert trajectories, especially if you want to train, like nowadays we have robots that go onto Mars or robots that explore volcanoes. You can't really train humans to design the paths for these robots because it's not safe to go into a volcano. But this is the closest intersection between reinforcement learning and supervised learning. And this class of algorithms, taking some information from human experts, kind of doing some supervised learning, but at the same time doing some reinforcement learning using algorithms that we'll see in a bit, they actually tend to perform the best for these safety critical real world applications. But yes, now let's go into the reinforcement learning aspect. So here are I'm going to first start by defining some important definitions in reinforcement learning. So these are called your state and action value functions. So starting with a state value function. So a state value function, we denote it as a V of S with a superscript pi, because these state value functions depend on what your current policy is. So what this V of pi of S basically means is that the expected return starting from state S and following your policy pi. So in other words, you're going to initialize your state st to be S, starting from this state S, and you're going to compute G of t, which you call is the cumulative long-term discounted reward. And then you're going to take an expectation over pi over all the randomness in a data set, because your policies might be random and your transitions might be random, as we've seen from MDPs. So essentially, this function tells us that if I give it a state and I keep following my policy pi from this state, what are the long-term expected rewards that I'm going to observe? And likewise, I can define it for action value functions. So instead of defining it for a state, I'm going to input both state and action. In other words, if I'm at this state and I start taking this action and I continue following my policy pi, what is the expected long-term reward that I'm going to observe? So very simply, this tells you how good your state or your state action pairs are under your current policy pi. And likewise, I can define my optimal state value functions and my optimal action value functions. Very simply, we saw that the previous state value functions and action value functions depend on a particular policy. If I take max over all possible policies, then I'm getting, oops. If I take max over all possible policies, then I can obtain the optimal state value function. So that means if I start from state S and I act optimally using the best policy, what is the expected long-term reward? And likewise, if I'm at state S and taking action A and following an optimal policy subsequently, what is the expected long-term reward that I'm going to observe? So the goal of reinforcement learning is really to find these optimal state value functions and optimal action value functions. So what it means to solve an MDP is that, given an MDP and a particular policy, I want to find the state and action value functions. So I want to be able to compute these two things for a given policy. And that's a prediction problem. And for the optimal control problem, it's very similar related. It basically involves another maximization over all possible policies. So this will involve finding the optimal policy that achieves your optimal value function and your optimal action value function. Just to summarize, so these value functions would measure how good a particular state or state action pair is for a given policy, and these optimal value functions will measure the best possible states or actions under all possible policies. So for state values, you have V pi and V star, and likewise for action values, you have your Q pi's and Q stars. So all these four terms are related to each other, your state value functions and your action value functions. We've seen that if you have a state value function for a particular policy, you can maximize over all policies to get the optimal one. And likewise, you can do the same for your action value functions. And what you can also do is you can interchange between your V stars and your V's and your Q's. So to go from your Q stars, I can take the best action, and that will give you my V stars. And if I have a QSA for a particular policy pi, I can take an expectation over this policy. So that would sum over all possible actions weighted by the probability of taking that action to get my state value functions for that policy. So all these are interchangeable. So again, why did I say that the whole goal of reinforcement learning is to find these Q stars and V stars? And that's because if you have a Q star, you can actually define, you can obtain the optimal policy. So I can take the optimal policy by simply finding the action that leads to an argmax over my Q star S and A. And that measures the long-term cumulative reward under the best possible policy. So if this action achieves this best long-term cumulative reward under the optimal policy, then that is the best action that I can take at this particular state. So you would take that action with probability 1 and 0 else. And you can also obtain the optimal policy with your V stars. So how would you obtain it with V stars? You actually have to do one step look ahead. So what that means is that, let's say you're in a particular state S, and as a policy, I want to evaluate how good each of my actions are. So for each action, I'm going to take it. And by taking this action, you're going to transition into a particular next state. And for each of the next states that you transition to, you're going to observe a reward. That reward from state S, taking action A and going to the next state. And once you go into this particular next state S prime, you can actually add up the discounted optimal value of state S prime under the optimal policy. So that's your V star of S prime. And together, these, under the expectation rule of all possible states S prime, because there's randomness in your transitions, this whole term will define how good your particular action is. And you want to take the action A that maximizes this term. Right? This essentially is a one-step look ahead. So if you're in state S, just having V star of S isn't really useful because you can't reason about any actions. But if you add v star of your subsequent states S prime, then you can reason about how each of these actions are, both in terms of your immediate reward and also your discounted future optimal rewards given by your v star of S prime. And just writing out these expectations, the expectation over S prime is basically averaging over S prime as given by your transition probabilities. So therefore, the summary here is that if you have your Q stars and your V stars, you can actually obtain your best possible policy, your pi stars. And therefore, the whole goal of reinforcement learning is to find these two values, your Q stars and your V stars, given interactions between your agent and the environment. So then the question is, how can we find these? So I'm going to start by going through three methods. Each of these three methods have different assumptions and different trade-offs. So the first method is called value and policy iteration. So what I'm going to do is that I'm going to look at GT. Again, GT is this object of interest, right? This is your immediate rewards times your discounted rewards into the future. I'm going to factor out gamma. And once I factor out gamma, I can basically rewrite this recursively as your GTs in the future. So what this value, the value of a particular state under a policy, what that basically is that the expectation over GT under your policy pi. So I can use my GT expanded into my immediate reward times gamma future rewards. And my expectation of the future rewards under pi is basically v pi of st plus 1. So what this term is I'm going to expand it out. The expectation under pi is basically summing over actions, each action weighted by the probability of taking that action. There's also an expectation over S prime, because each of these rewards, each of these state and actions that you take might lead to a different set of different next states. So this expectation over S prime is basically a summation over next possible states, your state transition from SA to your next state S prime. You're going to observe an immediate reward, and you're going to add a discounted value of the future states under your policy pi. So now I've been able to recursively write my value functions for a particular state S with respect to the value functions of future states S prime. And this equation is one of the most important equations in reinforcement learning. These are called your Bellman expectation equations. So just to make that more clear, we can also kind of derive it by picture. So it's very, very helpful to draw all these trees out, where these white circles are your states, and these black circles are your actions. So for each state, you're going to label your value function for that state, and you're going to have your value functions for subsequent states. And our goal is to really look at how the value function of state S interacts with your value functions of state S prime in the future. So how do you relate these two? Well, first of all, you know that at this state S, you might take many possible actions, right? In this case, there's two possible actions you can take. So I'm going to take an average over these two actions as given by my policy, right? My policy might say this action is 0.9, this action is 0.1. I'm just going to weight these two actions according to what the policy says. Once you've taken an average over your actions, let's say you went to here, this action, and then you have to take an expectation over your next states S prime. Because whenever you're in a state taking an action, you might transition into multiple next states just because of the randomness in the environment. So I'm going to take an expectation over my next states S prime. That's this red thing here. So that'll be summing over S prime multiplied by each of the transition probabilities to each of these S prime. P of S prime given S and A. And for each of these, you're going to observe an immediate reward that follows from going to this particular state S prime. And you're also going to observe a discounted value function of your next states. So that will be gamma v pi of S prime. So this is like a proof by these diagrams of how your v pi of S, your value functions for S, relates to your value functions for your next states S prime. And likewise, I can do it for my Qs. It's very similar. So now I'm starting from a particular action. Taking this action will allow me to go into multiple next states. So I'll take an expectation over these next states. For each of these, I observe and reward. And once I go into next states, there's also a set of possible next actions I can take. And that is given by an expectation over my policies over next actions A prime from this next state S prime. And for each of these actions that I take, I'm going to multiply it by the action value function at this next state and next action. And I'm going to discount it for future rewards. So again, this is how you relate your action value functions for a particular state action with your action value functions for your next states and your next possible actions. So why is this useful? So again, we have this one. We have this Bellman expectation equations that we just derived. In this case, I'm using the one for state value functions. What this is here is actually a linear system. So for all states S, there's this v pi, which is the object of interest, and everything else here is basically a linear transformation because your probabilities of state transitions are constants, your rewards are constants once you observe them, and for a given policy, this is also constant. So for a given policy pi, this is a linear system with your variables v of pi s for all s. And if it's a linear system with some variables and constants, what that means is that you can actually solve this exactly. So if you know all these constants and you know, and all these summations can be computed exactly, then you can actually solve exactly for your optimal, your state value functions, your v pi's for all states. And there's many different ways of solving it. One way of solving it is to solve it iteratively. So if this term appears on both the left-hand side and right-hand side, what I'm going to do is I'm going to initialize it to some value. I'm going to set it to be the left-hand side, to be the right-hand side. I'm going to compute it k plus 1 for the left-hand side. And I'm going to set this iteration back on the right-hand side. And then I'm going to compute k plus 2 on the left-hand side. It's an iterative method of solving these linear systems of equations. But the key here is that if all of these state transitions and your rewards and these summations are all tractable, then you can actually solve these state value functions exactly. And that is exactly our first algorithm. So the first algorithm would try to estimate these state value functions using this iterative method. So at iteration k, I'm going to set my state value estimates on the right-hand side and try to compute a k plus 1th iterate on the left-hand side. I'm going to iterate until I converge to the true values where both the left and right sides are equal. And this gives me my optimal state value functions for a given policy pi. So that gives me these values for a given policy pi. And then I'm also trying to improve my policy because my policy initially is also like a random policy, right? So for a random policy, I'm going to iterate such that left and right-hand sides are equal to get my optimal state values for a random policy. But my goal is to also improve my policy. So I'm going to take my policy at time k, and I'm going to try to obtain a better policy at time k plus 1. And I'm going to obtain this better policy by exactly using the estimates of my state value functions at time k. So recall this equation was how we went from given these, your state values, to actually your best policies using a one-step look ahead. Basically an argmax over actions, and with each action evaluated based on how good it is under your value functions. So this is an iterative algorithm. Your three variables here are again your policies, which are iterating k up to k plus 1. And for each set of policies pi, you're also going to compute your state value functions. And these two steps are known as policy evaluation. So evaluating how good a policy is. So given your pi's, evaluate your v's. And policy improvement. So given a good estimate of your v's at time k, try to obtain a better policy, pi k plus 1. And you're going to repeat these two steps until you converge. And at least in this case, where all of these are observable, your transitions and all, and the summations, or you can do them exactly, this is actually guaranteed to converge to your optimal policy. And this algorithm is known as policy iteration. And likewise, we can also do this instead of. So the problem here is that now we have to have two variables of interest. One of them being pi. So you have to both estimate pi and then go from pi to your v of pi. What you can also do is directly operate under your optimal state value functions. So instead of doing it for a particular value of pi, just straight away compute the optimal value. So that also involves us having to write our v star with respect to your v star of s with respect to your v star s prime. So for the Bellman expectation, what we saw previously, we actually summed over the leaves, right? We summed over this by taking an expectation with respect to a policy pi. But now we don't care about a particular policy. We care only about the best possible action. So instead of taking an expectation, you take a max. So your V star of S is equals to taking the best action, each of your Q stars. And you can write your Q star as an expectation over your S prime, your rewards, times your optimal state value function at the next state, given some discount. So what that basically means that you can first take a max over your action, and once you get to this part, you're going to take an expectation over the different states that you can end up in, multiplied by the reward, and a discounted value times your optimal state value functions for the next state. So again, this is how we can write my optimal state value function for state S with respect to my optimal state value function for state S prime. And likewise, you can also do it for Qs. I'm not going to go into in depth, but it's exactly the same thing. Whenever you have different possible next states to go to, you take an expectation, you add your rewards, and whenever you have a next set of actions to go to, you're choosing the best one. So instead of calling these Bellman expectation equations, because that was taking expectation over your policies, over your actions, now these are Bellman optimality equations, because now you're directly just optimizing and looking for the best action A. And again, we have two values of interest. We have your V stars of S and V stars of S prime on the left and right. We can again solve this by iterative methods, by initializing V star to be some number, some initial state, initial set of values. And then I'm going to put these values on the right-hand side, and I'm going to compute an update on the left-hand side. And I'm going to do this iteratively by taking something on the right-hand side, updating it to obtain the next value of the iterate on the left-hand side. I'm going to take this value k plus 1, put it back on the right-hand side, and try to get another update on the left-hand side for k plus 2. And that is exactly the next algorithm, which is very similar to policy iteration. These are called value iteration. So instead of working with policies, by estimating a policy first before converting the policies into the optimal one, I'm going to directly try to optimize for the best possible optimal state value function. So this was the inequality. This was the equality that we had. We know that they should be equal. The left-hand side and the right-hand side should be equal given by the Bellman optimality equations. And if they're not equal, we're just going to repeat this iterative process so that they are equal at optimality. And once you have this optimal state value function, I can just use a single computation to get the best possible policy. That's your pi star. So again, I'm going to repeat this until my policy converges. And if your state transitions and your rewards and your summations are all tractable, then you are guaranteed to converge to the optimal policy. Right. So again, you can do this likewise. Instead of doing your Bellman updates for your V stars, you can do it for Q stars. You get a different set of algorithms called Q value iteration. It's the same. It's just your preference whether you want to parameterize it using your V star of S or Q star of S and A. And that essentially gives us a summary of these exact methods. So what we've seen so far is that we've defined an MDP. We looked at the states, the transitions, the rewards, and we've derived two important set of equations. One is the Bellman optimality equations based on Q star and V star. And another set of Bellman expectation equations based on Q of pi and V of pi. The main difference here is that for Bellman expectation equations, you're given a policy pi, and you're evaluating the long-term expected rewards under this policy pi from a state or action. On the other hand, for Bellman optimality equations, you don't really care about a policy. You've already taken a max over all possible policies. So just given a state, you're computing the best possible long-term rewards under the optimal policy. So these values of interest, we've derived the inequalities for them based on these Bellman optimality or Bellman expectation equations. And we've seen how to learn these values, Qs and Vs, using Q value iteration or Q policy iteration or policy iteration. And we've seen that if these state transitions and your rewards are exactly observable, you can actually converge to the optimal policy. So that's actually the first set of algorithms. There's some limitations here. First of all, you actually have to initialize a value of your Qs or your Vs. You have to initialize these values for all states. And if you're working with Qs, you have to initialize it for all states and actions. So this essentially only works if you have small discrete state and action spaces. You can't really do this method if your states are images, because you can't possibly enumerate all possible images. And likewise, the update equations require fully observable MDP and exactly known transitions, which is usually a very strict assumption in the real world. So our next set of algorithms would actually extend these formulations. Instead of solving them exactly, we're actually going to try to solve them using function approximation. And we'll see how that helps us to solve MDPs with more uncertainty involving the transitions. So we recall, let's just look at Q-value iteration. What Q-value iteration did was that we first derived this Bellman equation, right? At optimality, we knew that your Q stars should obey this equation. And what we can do is, we derive this iterative method that initialize these Q stars to be some random initialization. And we're going to iterate Q star of K and compute Q star of K plus 1 on the left-hand side. So this equation is problematic because you actually have to do this exact summation over your states, your next states S prime, with your exact transition probabilities. So if you don't know these transitions, you can't compute this. So what can we do? So we can rewrite this Q-value iteration as, instead of an exact summation over your next possible states weighted by your transitions, I can rewrite it as an expectation over next possible states. It's given by the transitions. And if I rewrite it by an expectation, what I can do is that instead of computing the expectation exactly, I can approximate it just using Monte Carlo sampling. So what that would involve is, for any state action pair that you see, you're going to interact, you're going to start at a state, take an action, and the environment is going to return to you your next state, right? So you can collect a bunch of these next state action, next state pairs by just simulating and exploring in the environment. And that allows you to get a bunch of these triplets, S, A, S prime, so that you can actually approximate this expectation using samples. So just in the case of one sample, assuming you're just using like an estimate of using one sample, what you would do is that, again, in these iterative methods, you want the left-hand side to be equal to the right-hand side, right? So treat the right-hand side as your target, your reward plus your gamma discounted value functions for the next states. Treat the right-hand side as your target, and any error between the right-hand side and the left-hand side, I'm going to treat that as my error. So at optimality, the left-hand side should be equal to the right-hand side. So any excess difference between the left-hand side and right-hand side, I will treat that as my error. And you'll basically want to minimize this error towards 0. So how would you do that? Basically just compute the difference, treat it with your learning rate, and set Q of K plus 1 as your previous estimate plus alpha multiplied by this error. And this will slowly kind of tune your Q of K in the direction of this error, whether this was an overestimate or underestimate weighted by the learning rate, so that your Q of Ks and your Q of K plus 1 will follow this inequality. So here's actually a very easy extension to a new algorithm. So I'm going to start by initializing for all my states and actions my Q0, my initial estimate of my Qs. I'm going to start an initial state. I'm going to sample an action A and get a next state S prime. So if S prime is a terminal state, I'm going to treat my target as just a particular reward. So again, this is my optimality equation, right? So if S prime is already a terminal state, you're no longer interacting with the environment, then this all goes to 0, and your target is just your reward. Otherwise, your target is this term on the right-hand side. So the immediate reward that you observe plus your discounted values, expected discounted values in the future. And we know that at optimality, your left-hand side should be equal to the right-hand side. So any excess error would be the difference between your right and left hand sides. I'm going to treat that as an error, which I will then try to optimize for by this gradient-based method. It's not really a gradient-based method because you're not really taking gradients. So it's more of like a zero-order optimization method. So by choosing a specific learning rate and optimizing Q of k to be closer to Q of k plus 1, you're actually trying to minimize this error so that you're getting better estimates of Q star that respect this optimality condition. So this step here is actually really important. We've seen, we've seen that you're not actually able to compute this expectation exactly because you don't know these transitions, right? So you want to be able to sample a bunch of SA and S prime from the environment so that you can actually, can kind of approximate these expectations using samples. So how would you actually sample an action A? You could choose random actions all the time. You could choose actions that maximize your current value of your estimates, so basically your current policy, greedily. Or you could choose something that's epsilon greedy. What that means is that you would choose a random action with probability epsilon, and otherwise you would choose the action that best maximizes the current value of your action value functions. So this is actually a very important concept in reinforcement learning, that of doing epsilon greedy sampling of your actions. Why do you want to do that? So we know that initially your QSA, which you've just initialized, is going to be very bad. So following QSA would actually mean that you're taking a lot of suboptimal actions. And therefore, your bad initial estimates would drive your policy into very suboptimal regions. And you will never see subsequent states that you care about that give you good reward. So what is usually done in practice is that with probability 1 minus epsilon, you would choose the best action according to your current estimate of your action value functions. But otherwise, with probability epsilon, you would choose a random action. And you want to set this epsilon to be really high, maybe even 1 at the start. You're treating these random actions, so you're actually exploring sufficiently in the environment. And as your policy is being learned and keeping track of the good actions with good rewards, you would want to take these good actions under your policy rather than taking random actions in the future. So you're trying to gradually decrease your epsilon as your policy is being learned using this algorithm. So the best possible choice here is to do something epsilon greedy, starting with random action with probability epsilon, with epsilon really high at the start, and slowly decaying epsilon such that you're taking actions based on your current estimates of your action values. So this is essentially our next algorithm. This is a very simple extension of our policy and value iterative methods, so that instead of computing the expectations exactly, you're just taking a bunch of samples, so that you're taking a bunch of samples and computing these expectations approximately. And this is a slide from Berkeley's class. And the amazing result is that this actually converges to your optimal policy, even if you're acting suboptimally. So you're acting suboptimally because all these state and actions that you're sampling from the environment, they're based on your current estimate of your action value functions. And at the start, these are going to be very bad, right? You're only going to, with random chance, get into high good states with high rewards. So a lot of these states that you're going to be learning and training these Q values are going to be bad states with very low rewards. But still, you can actually show that this converges to your optimal policy, even if you're acting suboptimally based on the current estimate of your policy. And this is called off-policy learning. There's been a bunch of research in this. But again, these methods are quite hard to tune because you have to explore enough, you have to make the learning rate small enough, but not decrease it too quickly. And this exploration problem is exactly why we need to be careful of how to do epsilon greedy. We have to make sure that we are sampling actions randomly so that you're exploring the environment enough before you actually start trying to take actions under your current value of the policy. So this exploration is always a very big research question in reinforcement learning. How do you encourage your agents to explore the environment enough and find regions of high reward better than just randomly sampling actions? So this algorithm is called tabular Q-learning, or just Q-learning for short, but sometimes referred to as tabular Q-learning. So why is this called tabular? So it's called tabular because you're initializing for all states and actions your QSAs. So what that means is that you want to keep a table that has number of size of S rows and size of A columns. So you have this table where each entry is QSA for a particular state and action. And this is still not ideal because it can only work for small and discrete state and action spaces. So again, if your states is images or your actions are continuous, then you can't really do this. And again, you can't really generalize to states that you've not seen before. So you will only be, everything here, you'll only be learning these estimates, your Q estimates for S and A for states and actions pairs that you've seen. So you're not going to be able to generalize to new states. So how can we solve that? So the next algorithm, we're going to see that in the next algorithm, but before that, let's just summarize this tabular Q-learning real quick. We started with MDPs with unknown transitions. You can't really compute this exactly. We're going to still use these Bellman optimality equations as given by this. So the optimality, these are equal as derived. And instead of computing this expectation exactly, you're going to replace this true expectation with estimates. So what that means is that you're going to sample a bunch of S prime just by exploring and simulating your environment. You have to make sure it's epsilon greedy so that you explore enough and get states of high reward. You know that this is your optimality equation. At convergence, the left-hand side should be equal to the right-hand side. So any divergence between the left and right-hand side, I'm going to treat it as my error. So this part will be your error. And you're going to optimize for this error using zero-order gradient methods by defining a learning rate and updating your Q of Ks to be closer to your Q of K plus 1s as weighted by the amount of error that you're currently making. So that is essentially tabular Q-learning. Again, the issue is that it's tabular. It requires small and discrete state and actions, and you can't generalize to unseen states. So how can we solve that? So now we're going to our last algorithm for the day, and that is extending tabular Q-learning to deep Q-learning. So using these high-level, using these recent deep neural networks with function approximation and combining them with Q-learning. So the goal here is to use these neural networks to be able to extract informative features from these high-dimensional input states, such as these images, so that you can actually do Q-learning instead of having to iterate over all states and actions. So the idea here is very simple. Instead of defining a QSA as a table over all states and actions, I'm going to amortize it by just learning a set of weights W. So this set of weights W would take in a state and take in an action, run it through some parameters W, and output QSA given W. The other alternative is that just taking a state, run it through some parameters W, and output your QSAs for all actions, across all your action spaces. So essentially the goal here is, this works very well. And this is a very simple extension because instead of storing this table of all your QSA values, I'm just going to try to learn this table directly by taking in states and actions and learning just one set of parameters W. And this works for high-dimensional continuous states. If you have an image here, you can appropriately choose your convolutional networks. If you have states being both images and text, you can use your convolutional networks and your transformers. And you can also generalize to new states. So we know that deep networks, these function approximators, they can generalize because if you give it one particular image and you give it a very similar image with similar semantic concepts, you'll most likely make similar consistent predictions. So likewise, using these function approximators also allows you to generate to new states that are similar, but not exactly the same as the ones that we've seen before. So how would you train such a model? Again, you don't have these labels. These can't really train using supervised learning. So how would you train it? Training it actually involves many of the similar ideas as Q-learning. So again, you have these Bellman optimality equations, right? That relate your optimal Q star with your optimal Q star and next states and next actions. We know that we want to learn these Q stars such that this holds exactly. So you're going to start with a particular set of weights where these left and right side are going to be different because you're going to start with a random set of weights. You're not going to obtain this optimality condition. So again, whatever the difference is, I'm going to compute the difference. I'm going to treat that as a loss function. So in other words, treating the right-hand side as a target, computing that, and basically the left-hand side should match the right-hand side. And any difference, any squared difference or absolute difference, I'm going to treat that as my error and try to minimize that to 0. And if I do minimize it to 0, then these Q values should respect these optimality conditions. So we've seen that a method similar to this, if I use like a table lookup for your Q stars S prime and A prime, it converges exactly. That was your tabular Q learning method. But if you kind of replace it, if you go from a table lookup method to one of these methods that you learn these parameters W using your neural networks, it's actually much harder to train. So obviously you no longer have these convergence guarantees. And sometimes it might also diverge. And there's two main issues, two main details that we have to fix before we can actually get this function approximation methods to work. So one thing is that problem of correlations between samples. So let me draw an analogy. So when you want to train for image classification, and you have maybe different categories, you have your cats, your dogs, your humans, your tables, and so on. Every batch which you want to put into your neural network to train these image classifiers, they should contain an equal sample of these different categories, right? That basically means that the samples I put into my neural network should be as uncorrelated as possible, so that you can best learn a classifier across different uncorrelated samples that you want to classify in between. You want to classify with respect to. And if you just do this naively by neural networks, so you're going to get a lot of correlations between samples. So why is that? So you're going to start with S, you're going to observe a next state, you're going to take action A and observe a next state. So that is one particular data point, your S, A, S prime that you're going to give to your model. And then you're going to start from this S prime, treat that as a next state, take another action and go into another state. I'm going to treat that as a next data point. I'm going to take that next action, take another next state, get another next action, and put that into the model. So all of this sequence of S, A, S prime, your data points, that you're giving it into the model, these are all extremely correlated because they are from the same trajectory. They're from subsequent states from the same trajectory, right? So they're almost exactly very highly correlated. So that's one reason why it might not work. Another reason why it might not work is that problem of non-stationary targets. So again, if you look at image classification, for a particular set of images, your labels are always the same, right? You've labeled your data set once, you never change the labels, and you just iterate through the data set multiple times to learn a good classifier. But what's happening here is that we've kind of treated our right and left-hand side as the target, the difference between the right and left-hand side as a target. But every time I update my parameters W using gradient descent, the same targets for the same states and actions are going to change, right? So if I just keep my state and action constant, my initial value of W is going to give some value of your Qs. If I update W using gradient descent, I'm going to get another value of your Qs. I'm going to get different values of my Qs each time as my weights are getting trained. So that essentially has the analogy of doing image classification, but your labels are changing all the time. And right now I'm labeling this as a cat, and for the same image, a few epochs later, I'm going to label it as a dog. So this is a problem of non-stationary targets. And again, that makes it very difficult to train these models. So empirically, there have been two solutions proposed. Firstly, to remove correlations, a very easy method is to just first start by collecting a bunch of samples. So one trajectory would take S1, A1, observe next reward, the next state, and then from the next state, take next actions, next reward, next states. I'm going to collect all these trajectories before you even start training. And then I'm going to put it into a data set. I'm going to shuffle it, and I'm going to sample a random mini batch of transitions. So by shuffling and sampling a random mini batch, then I'm going to decrease my correlations between subsequent data points that I give into the model. Again, when you're collecting this data set of experiences, which we call the experience replay, it's important to explore and use epsilon greedy methods. So at the start, maybe before you even start training the model, you will just collect a bunch of random states and actions. And your hope is that, for some of these, you're going to have high rewards. And those will be informative in training the model. And then as you slowly train your model and you get better estimates and you get better policies, then you can decrease the value of your epsilon and rely more on the current value of the policy as given by the model. So more of these state action reward pairs should have high rewards. And you're going to constantly kind of update your experience replay buffer. So that's the first thing. That's to remove the effect of correlations. The second thing, which was that of non-stationary targets. So the idea here is that you're going to you're going to fix some Q targets. So whenever I sample a random mini batch, I'm going to compute one of these targets. So in this case, the right-hand side, using W minus. So W minus is a set of old parameters that I have fixed maybe a few hundred, 1,000 epochs ago. So I'm going to fix these. This set of W minus parameters is not trained. These are that give my targets. And I'm just going to train my parameters W that give the outputs to my model. So keeping the targets fixed with a fixed set of old old network parameters. And I'm only going to update the network parameters that gives you the output of your model. So this, to some extent, can help you reduce your non-stationary problem because now your targets are fixed. They're no longer changing. And after maybe 1,000 iterations, then I'm going to replace my W minus with W. So I'm only going to do it every 1,000 iterations. So this is the method of using fixed Q targets to better reduce the problem of your non-stationary targets. And this is actually a very, very useful algorithm, I think. This was one of the main algorithms that contributed to the success of deep reinforcement learning recently. And because this method, by combining your Q-learning methods with your function approximators, your deep neural networks are able to do many tasks very well. So for Atari, for example, they've come up with these like convolutional networks that take in these images. So these are all these games that are really high-dimensional images that you can't possibly train using tabular methods. But by using convolutional networks, you can actually learn very informative features that allows you to learn quickly and generalize to next states, to different new states. So one thing to take note of is in their method, instead of just giving it a single frame, a single frame for S, they actually stack raw pixels from the previous 4 frames together. And what that does is that it actually encourages the Markov property. You can think about why that's important. So just to give some intuition. So let's say you have these like these games like Breakout, where you have to not only keep track of the current state of the ball, but you also have to keep track of the trajectory of the ball. So it's whether it's moving up or moving down. So like a single state of the ball isn't enough. So the designer method that actually respects this Markov property, you can actually take the previous 4 states. I mean, ideally you would take all previous states, which up until the Markov property holds. But I guess in practice, you can't take a bunch more states. 4 is like a reasonable number. So if you take 4 states, you can actually track the position of the ball over the past 4 frames. And that actually allows you to predict the next state and next action accurately without relying on information from frames even before that. On the other hand, if you just have a single state, you're actually not able to predict the next state or next action because it does not respect the Markov property. So if you have a single state, you actually need to depend on the previous state before that just to even know where the trajectory of the ball is going up or down, right? So just keeping one state doesn't actually respect the Markov property. So this general method, these deep Q networks do really well. These are all the Atari games. Some of which, if you look on the left-hand side, these are like 3,000% better than human performance. And these are usually the games that requires reaction speed. So, obviously, training these AI, they'll have excellent, almost perfect reaction speed. They also have a short-term reward. So if you look at this game, you're always observing reward whenever, within like a few frames, you're observing reward from breaking out these tiles. And you don't need that much exploration. So these are perfect settings where deep RL works much better because they're very good at exploiting short-term reward, and it's very difficult for them to explore, and they definitely have much better reaction speed as compared to humans. So these settings, deep RL is much better than humans. On the other hand, you have these games like Montezuma's Revenge where performance is still at 0%. This was in 2016. Obviously, nowadays there's better methods, but at least these vanilla DQNs, performance is still at 0%. And why is that? Because these types of games have super long-term reward, requires a lot of exploration, and also requires knowledge of these complex dynamics. So these games actually involve things like, picking up a key and opening a door and going up a ladder. So humans know that, you want to pick up a key to open a door. But for AI that's trained from scratch, you don't know that. They don't know that. So these are much bigger challenges for DeepRL. But recently, I think 2019, they've also been able to come up with much better methods for playing these games. So now you see, picking up these keys and waiting for these barriers to open and picking up these jewels. And obviously, these are not just vanilla deep Q networks. A lot of these methods are based on maximizing curiosity. So curiosity can be seen as, giving the model external rewards instead of just relying on the super sparse rewards in the environment, right? So curiosity is one method of just asking the agent, how well can I predict my environment? So if I cannot predict my environment well because I've never seen it before, or because it's stochastic, or because I don't know the dynamics of the environment, I should perhaps explore that region more. So curiosity and all these other auxiliary reward methods have emerged as strong methods to kind of supplement the rewards so that you can better train your models. Cool. So just to summarize, we've gone through a lot today. So what we started with was these fully known Markov decision processes with perfect states, transitions, and rewards. If you knew all of these, you could define this set of equations, both Bellman optimality equations. Those are equality equations involving your Q stars and V stars, which, given a state or action, tells you the expected long-term reward under the optimal policy. And likewise, we also derive these Bellman expectation equations, which under a state or a state action, compute your long-term rewards under a particular policy, pi. And we showed how to solve these, either through these value iterative or policy iterative methods. And if you know all these MDPs exactly, they converge. But the limitation is that it only works for small and discrete state interactions and requires known transitions. And we also saw an extension of how we went from perfectly knowing these transitions to actually sampling states and approximating these transitions, approximating the expectation through samples. And the idea there was to do tabular Q learning. So the problem there is that you still have to keep a table of your states and actions, which still requires small and discrete state and action spaces, but at least you can do it for MDP to unknown transitions. And then we finally saw how we can extend tabular Q learning to work with function approximations. But instead of keeping a table of all your states and actions, your Q values, you're just going to learn one set of parameters W that amortizes the prediction of your Q essays. And again, the training procedure is the same as Q learning, which is that for this optimality equation, I'm going to treat one side as a target and treat one side as your current estimate, and try to minimize this difference using gradient descent, so that at optimality, you're estimating your Q stars where you're respecting this Bellman optimality equation. And we saw two main issues, one of which was you need to use an experience replay so that you don't have correlated samples. And you also need to use fixed Q targets so that you don't actually have this non-stationary prediction problem. And deep Q learning actually works for these high-dimensional states and actions, and also generalizes to these unseen states. Cool. So we have about 10 minutes left. Let me just give a brief introduction to some more applications, especially language and RL. I think this is what people are mostly excited about. But we're going to continue most of this next lecture. So a lot of these categorizations are from this very fantastic review paper at HCI 2019. It's the survey of reinforcement learning with natural language, and that is one of the required readings for this week. And essentially, what they've done is that they've kind of classified all sets of possible tasks where we have language and reinforcement learning. So one of which are task-independent methods, and the other set are task-dependent methods. So in task-independent methods, the task actually doesn't require language. It's just that we are giving the model, giving these agents some initial information that is pre-trained with language and vision. So for example, giving it word embeddings that tells it what these keys and skulls and ladders and ropes are. And the other set are more like task-dependent methods. So for task-dependent methods, that means that when you're actually in the environment, you have language provided. So language is given dependent on each task. And again, there's two categories here, one of which are language assisted and one of which are language conditional. So I think the easiest way to think about these is that for language assisted, you basically can solve the task without having language, right? If you look at these, you can kind of solve these environments. It's just that these language instructions that you're provided with, they assist you in solving the task, right? It gives you more information about keys and they give you more information about skulls. But if you don't have this information, you can still conceivably explore. It's obviously going to be much harder, but you can still explore and solve these tasks. Language conditional, on the other hand, basically means that you have, the task is only defined if you have language, right? Because in this case, you're given an explicit instruction, such as like going down the ladder and walking right. So the task is not even defined if you don't have language. So these are more language conditional tasks. So we're going to look a bit at these both language conditional and language assisted. I think these are the main environments that have both your visual inputs and also some description. So for language conditional RL, there's three main classes, instruction following, getting rewards from instructions, and language and observation and action space. So for instruction following, you have these tasks, we have this environment, and you're just given these very simple instructions, which you have to train an agent to follow. So just go to the green torch. And the main difficulty here is that, during training and testing, you're actually given different sets of objects that you have to go to. Otherwise, the agent can kind of just memorize what each of these objects are. So the main research problem here is you have to do fusion. You have to kind of fuse your language and visual information. You have to align. You have to kind of look at each of these. You have to understand each of these descriptions and actually match them with what they're aligning with in the environment. So there's been a bunch of methods proposed for this. Essentially, again, you can set up these MDPs where an agent is interacting with an environment, is taking actions, and is seeing states where the state consists of both images and text. And you're going to get positive reward if you get it, or otherwise negative reward. So they've come up with many methods. I think this was a very popular method, which essentially does gated attention. So getting image representations and given text representations, getting a gated attention that learns a multimodal representation before you can apply basically any policy learning module. It can be deep Q learning. It can be like policy iteration, value iteration, any of these policy learning modules that we've seen in this lecture and that we'll also see in next Thursday's lecture. And they've actually shown that these methods are quite useful. So this gated attention method can actually effectively go to these different types of objects. Even when there's occlusion, right? Sometimes, so for easy, you have all of them presented to you. For medium, there's some clutter of objects. And for difficult ones, you actually only have partial observability. So you might have to might have to turn around and walk a bit more before you actually see these rewards. And they also found that different representations actually they actually learn different representations for different attributes. So grounding, basically. So by seeing blue armor and by seeing red pillar, they can actually generalize to blue pillar. And why is that? And that's because they've learned separate representations for your color and your objects. And therefore, you can generalize to new objects of different colors. Cool. So other methods have also been proposed. I think this is a method that actually gives you more instructions so that you can get more rewards. So for example, you have, this Montezuma's revenge paper. It's a really difficult environment. If you just let the agent explore, it's not going to learn anything. But what you can do is you can get people from Amazon Mechanical Turk to play the game and describe certain entities that you should observe while succeeding. So you actually give instructions like jump over the skull or going to the left. And if you actually succeed in solving these intermediate goals, normally if you jump over and go to the left, you're not going to get any reward from the environment, but you can define these external rewards based on how well you can execute these intermediate instructions. And these can speed up learning. Yeah, so again, you can look more about in the paper, but essentially it encourages, it takes in these sequence of past actions and also these states that it's currently taking in, and it's also going to give it these external descriptions, and it's going to give rewards based on whether they've executed these external instructions successfully, and it shows that this speeds up training much better. And the last one, just one last thing before we finish. The other method is also based on instruction following, except that now you have much more long-term goals, and you're also doing this in a QA setting. So you're going to start with a particular robot agent in some environment, and you're going to ask a question. So what color is the car? So again, it's not going to see it immediately, but it has to do things like turn around. So I think this is a failure case. It wasn't able to actually reach there. It actually went outside the house to reach it. But yeah, so essentially it's partially observable. It has to maybe take some steps around the house before it can actually see the object in question, before it can actually provide the answer. Cool. So let's stop there. So today, we talked a bit about language conditional RL. Next week, we'll continue on how language can assist reinforcement learning for both domain knowledge and structuring policies. And we'll also talk about how we a different set of reinforcement learning methods based on policy gradients. Yep, so that's it. Here's a main summary for Deep Q learning.